With MSU's high-performance computing center producing large amounts of heat, a cost-effective way to cool the computers is required. Conventional refrigeration techniques are effective but costly. An alternative method of heat transfer is with the shell and tube heat exchanger, which are used in many commercial applications. The HPC outputs around 1 megawatt of power which needs to be dissipated. The available cooling water flows from a reservoir at 57 degrees Fahrenheit at a rate of 1 million gallons per day and should not exceed 60 degrees Fahrenheit when leaving the exchanger. The hot stream from the computers is assumed to be leaving with a maximum temperature of 100 degrees Fahrenheit. Lastly, the heat exchanger should be 20 feet or less in length.
The Aspen software was utilized to design a suitable heat exchanger with the given parameters. It was decided to optimize the outlet temperature of the heated fluid by varying the mass flow rate of the hot side detailed in the process inputs figure here. The tube side of the exchanger was determined to be the hot stream and the fluid was set as propylene glycol. Propylene glycol is an excellent antifreeze fluid which provides safety from MSU's cold winter climate and when compared to water is non-toxic, which is a benefit because of its use near potable drinking water. The material of construction for the shell was made to be carbon steel because of its relatively cheap price compared to other metals. The tubes were specified as copper because of its high thermal conductivity when compared to carbon steel. Copper also has better corrosion resistance than carbon steel. Utilizing copper raises the price, but comes with the benefit of better heat transfer and mechanical properties. The geometry of the heat exchanger was determined by selecting a standard tube size of 1/2 inch and packing them together efficiently with a 5/8 inch pitch and a 30-degree triangular configuration. Through an iteration process, the following results were obtained. With this heat exchanger design only transferring 0.296 megawatts of heat, a total of 4 heat exchangers would be needed to fulfill the 1 megawatt HPC output. A propylene glycol flow rate of 105,000 pounds per hour was able to produce an exchanger that was slightly under 20 feet and provided delta T of 27 degrees Fahrenheit for the hot stream coming from the HPC. This allows the propylene glycol to be cycled back through the HPC and absorb a significant amount of heat due to the high delta T potential. This was done all with a delta T of the cold stream of 3 degrees Fahrenheit. The pressure drops were kept relatively low at 11.1% in the shell side and 2.9% in the tube side.
The figures below summarize the cost, weight, and spatial geometry of the design. The price of one heat exchanger was calculated to be about $59,000. Additionally, since the heat exchanger might be subject to fouling, cleaning the system was considered. The shell could be cleaned with a safe solvent flush, whereas the tube side containing the propylene glycol could be cleaned mechanically with a water jet. From a search for potential suppliers, we found these heat exchanger manufacturers suitable for our application.